All right, folks, we're looking at section 1.3 today. We skipped section 1.2 because ain't nobody like section 1.2. No, it's because of the standards that standard was taken out in the state of Florida. So they're like, nah, that's not important. So we're like, okay, cool. We'll just skip it. So 1.3, reporting with precision and accuracy. Okay. So the essential question, how do you use significant digits when reporting the results of calculations involving measurement? We're going to get to significant digits probably in the next video. I was looking at this section and it's a very, very, very long section. So yeah, we'll see how things play out. Here we go. Comparing precision of measurements. So numbers are values without units. They can be used to compute or to describe measurements. Quantities are real-world values that represent specific amounts. For instance, 15 is a number, but 15 grams is a quantity. Okay, precision is the level of detail of a measurement determined by the smallest unit or fraction of a unit that can be reasonably measured. I'll talk about that a little bit more detailed in a second. Accuracy is the closeness of a given measurement to the actual measurement or value. Suppose you know the actual measure of a quantity and then someone else measures it. You can find the accuracy of the measurement by finding the absolute value of the difference of the two. So precision is basically to what level you're reporting at. So for example, I want to give you kind of a representation. Let's say you have a ruler, okay? You have a ruler, 1 inch, 2 inch, 3 inches, 4 inches, 5 inches, 6 inches, okay, whatever. That's a whatever ruler, and you're measuring some kind of stick, right? Okay, we'll say a stick, right? We'll say it goes to there, okay? So here's what precision is. One person might say that stick, if we have 1 inches, 2 inches, 3 inches, some person might say that stick is about 3 inches long. And then another person will say, you know what? Well, it's a little bit past 3 inches. It's really more like 3.3 inches, right? The 3.3 inches is more precise because it's going down to that extra measurement. Think of it like the 3 inches. The guy who said 3 inches is kind of rounding it a bit, right? So the more you round, the less precise you are. So the more detailed you can be, the more precise you will be. So 3 inches and 3.3 inches, when you compare them, 3.3 is more precise because it's like, let's say, less rounded, right? The more you round your number, the less precise it will be. So that's what we're looking at when it comes to precision, is who went a step further to be a little bit more precise. So when we look at these here in A, complete the table and choose a more precise measurement. So here we have two measurements. We have 4 grams and then we have 4.3 grams. Now when this box here says smaller unit, we're looking for what unit is not rounded in a sense, or what decimal place does it go. So when I'm looking at, let me see if I can draw like a little chart up here. Let's say we have these numbers. We'll have a decimal. We have tenths, hundredths, thousands. So tenths. Oh boy, I don't make this big enough. Tenths. This would be hundredths. I'm just gonna say that. This is gonna be. I can't write words. Thousandths. Oh man. I can't make this. Anyway. So whoever goes basically to more decimal places, the more precise they are. So 4 grams, that person has only gone to the tens place. They've only gone here because they don't have any decimals. Whereas the 4.3 grams, they've gone to the 10th place. They've gone once over to the 10th place. So because they've gone, further to the right, you can say, they are being more precise. Just like I mentioned in my first example with 3 and 3.3. This person has gone to a little bit more detail to say 4.3 rather than just 4. So the smaller unit is a tenths place. So we're going to put just the 0.1 to say, or you can really just say, we should really write it like this, 0.1 tenths place. Okay. So the more precise measurement is therefore the 4.3 grams because it went to the tenths place. Now, if we look at the second one, we have 5.71 ounces and we have 5.7 ounces. So the first measurement has gone 2 decimal places over to the hundredths, and the second measurement has only gone 1 decimal place over. So we're looking for the one that's gone into more detail, which is the first one. It's gone more decimal places over. It's gone all the way to the hundredths decimal place. So that one is the one with the smaller unit, the 5.71. It has gone to the hundredths place. Okay, therefore it is more precise than the one that only went to the tenths place. So that would be the more precise measurement is 5.71 ounces here. Now, the third one is very tricky in the sense that you have to pay attention to the fact that these are different units, meters and centimeters. So one thing that's helpful is to convert these into the same units. Converting them to the smaller unit is more preferred for precision purposes. So 4.2 meters, you might have somewhere in the book. We'll have to see if it's somewhere in the book. But a thousand, oh boy. Oh, not 1,000. Can you stop moving? 100 centimeters equals 1 meter. So if this is 4.2 meters, well, multiply that by 100, and it's actually 4,200 centimeters. So now, oh my gosh. All right, now we can really compare these two. So this one only goes all the way to the hundredths place here, but this one, 422, actually goes all the way to just the single digits place, right? The ones place. So when you're comparing the two, this one goes to the hundreds, this one goes to the ones, then the one that's going to the ones is more precise because, again, it's further down the line here, right? Remember, the hundreds place is the third one there, and the ones place is here. So the ones place wins. The ones is more precise. I wrote the wrong number, by the way. 4.2 meters is 420 centimeters, not 4,200. I kept thinking 1,000 for some reason. I don't know why. Probably because I was so bothered about trying how to spell it earlier. Anyway, this one is so it's actually, this one actually goes to the tens place, whereas this one goes a step further and doesn't really round it and goes all the way to that ones place. So the ones place, is a little bit more precise here. So that makes the 422 centimeters a bit more precise. All right, and then the last one we have is 7 feet 2 inches and then 7.2 inches. So again, it's a little bit deceiving because this one is strictly inches, whereas this one's kind of in feet, and then inches. So how many inches really is 7 feet 2 inches? Well, remember, there's 12 inches in a feet, so 12 times 7, and then add the 2 extra inches to it. So 12 times 7 is 84. So 84 inches plus 2 inches. This is really 86 inches here, whereas this is 7.2. Now, 86, remember, only goes up to the ones place, whereas 7.2 goes all the way over to the tenths place, making the 7.2 more precise because it's gone further into the decimals, if you will. So it's very much similar to the first one, where, hey, this one's gone to the tenths unit. Oops. And that is therefore more precise than the one that only went to the ones place. So it sounds confusing when I say it. I don't think I'm doing too good a job overall trying to explain this, but just a quick recap to kind of sum it up. The further you can go, or you see a number, when you're comparing two numbers, the one that uses up more decimal places or is further to the right on this scale is the one that's more precise. So when you saw 420 centimeters, then it really stopped being precise here, right? Because it sort of rounded off in the end. But when you say 422 centimeters, well, now you've got this number here to be a little bit more precise with. Okay, because when you just have that as being 0, then you're kind of stopping your significant digit at this point. But when you do go ahead and say it's 422, you're continuing on further to the right, making it more precise. So when we look at these, you saw the first one was 4, right? Just 4. And then the one over to it was 4.3. So 4 was nice, but 4.3 was better because the 0.3 has gone to the tenths place, whereas just 4 was only in the ones place. So the one that goes over to the tenths place wins because it's further over to the right on that scale. And again, 5.7 compared to 5.71. 5.7 goes to the tenths place, but 5.71 goes to the hundredths place, which means obviously 5.71 has gone further to the right on the scale and therefore wins in the more precise measurement category. Okay. And again, 86 inches. The significant digit here is the ones place. It ends at the ones place, but 7.2 inches, although it's not even comparable, 7.2 inches, 7.2 at least goes to that tenths place. It goes into the decimals. So again, it's further to the right on that scale, so it wins the more precise measurement battle. Okay, so Eric is a lab technician. Every week he needs to test the scales in the lab to make sure that they are accurate. He uses a standard mass that is exactly 8 grams and gets the following results. So now, complete each statement. Well, first let's look, scale 1 is 8.02 grams. Scale 2 says 7.9 grams, and scale 3 says 8.029 grams. The statement, all right, so the measurement for scale blank is more precise. So which of these is more precise? Now remember, precise is just going to that level of detail in the decimal. So when we're comparing these, right, I saw my scale up there. Let's use that scale up there. We have 8.02. Let's I'm going to use that scale, but I'm going to write it down here so I can write them all next to each other. We have 8.02. We have 7.9, and we have 8.029. So the first one goes to our hundredths place. The second one goes to our tenths place. And the last one goes all the way to the thousandths place. So since the last one goes all the way to the thousandths place, and it's got more significant digits as far as more detailed decimal values, the last one is more precise because it goes to that extra extent. It goes 1 decimal place further than the other 2 options. So scale 3 is more precise. because it goes to 3 decimal places, and that is the furthest out of the 3 scales that we were given. Because it measures to the nearest, as we just mentioned, it goes all the way to the thousandths place. Remember, that's tenths, hundredths, thousands. Okay. Which is smaller than the smallest unit measured by the other two. When it says smaller, I can see people getting confused when they say smaller. It just means more level of detail. It's obviously, as you go further to the right, you're dealing with smaller numbers. That's kind of what they mean. Like, you know how 0.01 is technically smaller, 0.001 is technically even smaller because you continue to go further to the right. So that's what it means. When it says smaller, it's I kind of say it as is further to the right of the decimal. That's kind of my translation of the word smaller in that extent. I'm going to erase this because I need this to be blank. Okay, we'll come back. We'll erase that later. All right, so find the accuracy of the measurements in step B. So remember, accuracy is how close it is to its actual measurement. And in the problem, it said that the actual measurement was 8 grams. So basically, whichever one of these is closest to 8 grams will be more accurate. So scale 1 was 8.02. 8.02. Scale 2 was 7.9. And scale 3 was 8.029. So whichever one of these answers is the smallest number would be the most accurate number, right? So when I subtract 8 minus 8.02, I get negative 0.02. But because you'll see these absolute value bars, the absolute value bars will make that negative a positive. So when you see the absolute value bar, all the answers should just be positive. So the answer here is 0.02. So technically, just to say that it was 0.02 off. All right, the next one is 8 minus 7.9, and 8 minus 7.9 would be 0.1. And the absolute value bars, again, are here. They just make it positive. It's already positive, so it doesn't really change. It's going to just be 0.1. And now the last one, we have 8 minus 8.029. That absolute value comes to be negative 0.029. But again, the absolute value just makes it positive, so it's really just 0. Let me put a 0 there. 0.029. So now the question is, okay, what's the order here? Which one of these is actually smaller, or the smallest one? So if we actually put them in order, the biggest one is 0.1. Why is this the biggest? Because this is a tenth, and these start at the hundreds. So this starts at the tenths, these start at the hundreds. So the ones that start at the hundreds are going to be smaller. For example, think of this as 0.100, right? And then the second one, or I'm sorry, this one here is really like 0.020. And then the last one is like 0.029. So technically, if it helps, make them all the same amount of digits. So yeah, let's do that. That might actually help. So this is really like 0.020. We're going to make it, because I see that this one goes to 3 decimal places, I'm going to do that with all 3 of these. So if I make this number 3 decimal places, then I just put a 0 at the end of it, and it's got 3 decimal places. Now to do that with the second one, 0.1, I have to add 2 more zeros to the end of it to make it go 3 decimal places. And then the last one obviously already has 3 decimal places. So now it's easier to order them because you can kind of look at it like it's 20, 29, and then 100. And that's exactly what the order would be. So this one is the smallest, so it's first. It's the most accurate. This one is the next smallest, so it comes in second. And this one's definitely the largest, so it comes in third. So that's how I would like to do it. I think it's helpful when you look at them all kind of on the same system, on the same scale, but all three of them being, 3 decimal places out. Then I can just look at it kind of like at normal numbers. So yeah, 20 is smaller than 29, and 29 is smaller than 100. So, right, 20 is smaller than 29, and which is smaller than 100. So that goes same thing with decimals. So 0.020, 0.029, and 0.1. Same way as those regular numbers work. So yes, the most accurate one was scale 1, which is the 8.02 grams. Is the most accurate because, well, I mean, I've kind of already explained it up here. Is most accurate because, as basically this reason right here. 0.02, I'm going to go ahead and write it like that just for the sake of it, is smaller than 0.029, which is smaller than 0.100. Yeah, because remember, 20 is smaller than 29, which is smaller than 100. So that's my thinking anyway. That's how that works. So discussion. Given two measurements of the same quantity, is it possible that the more precise measurement is not the more accurate? And that is, yes, it's possible. And we just talked about that because the more precise measurement was scale 3 because it went to a third decimal place. But scale 3 was not the most accurate because it was just a little further away from 8.000 than, the most accurate one, which was 8.02. So it's possible that you can be more precise, but not more accurate. Okay, determine precision of calculated measurements. So as you have seen, measurements are reported to a certain precision. The reported value does not necessarily represent the actual value of the measurement. When you measure to the nearest unit, the actual length can be 0.5 unit. This is very important right here. Less than or 0.5 units greater than the measured length. So a length reported at 4.5 centimeters could actually be anywhere between 4.45 and 4.55 centimeters, but not including 4.55 centimeters. It cannot include 4.55 centimeters because 4.55 centimeters reported to the nearest tenth would round up to 4.6 centimeters. Calculate the minimum and maximum possible areas. Round your answer to the nearest square centimeter. So let me go back to this whole 0.5 unit less than and 0.5 unit more than. The key to this is the word unit. That can be the reason why this might get confusing to some of you. But the reason it says, okay, so it used the example 4.5, right? Here's what I would do. When it means half a unit, it means half a unit of a tenth, because we have, in this scenario, we're dealing with tenths, that 1 decimal place over. But half of that is actually moving over to the hundredths place. So think of it like this. Think of that 4.5 as really 4.50. So we're going to do this with all of these measurements. We're going to go 1 decimal place further. We're going to put a 0 there, 1 decimal place further. And then we take a 5 off of one end and a 5 off the other end. 5 less than this and 5 more than this. So if we go, I'm trying to think how to say this. 4.5 is right where our measurement was at. But half a unit less than that would be 4 point, well, we would subtract 0.05 from it to get half a unit less than, and we would add 0.5 units to it to have the max side. So the min side is half a unit less, the max side is half a unit more. So the min side is 4.45, and then the max side is 4.55, as it mentioned here. So here's the trick that we're going to do. We're going to take whatever decimal we have, right, like 4.5, tack on one more decimal place to it with a 0, and then use that decimal place as our half unit measurement. So we're gonna, when we subtract and add, we're gonna go that decimal place over and subtract a 5 and on once, and then add a 5 on the other, but only in that decimal place, only in that one decimal place further over. I know it seems kind of weird, but let's go through a couple examples. You'll see what I mean. I'll be right back. If you want to skip ahead in the video about 30 seconds, I got to go blow my nose. So I'll be back in just 1 second. Okay, so let's look at the example here in example A. So example A, find the length and width of a book cover that's 28.3 centimeters and 21 centimeters respectively. So the length is the 28.3 number, and the width is the 21 number. Okay, find the range of values for the actual length and width of the book cover. So we're going to find the minimum length and maximum length, and the minimum width and the maximum width as well. So let's focus you can see all the numbers broken down. It's already worked out completely for you, but let me explain my process for it. So let's start with the 28.3, right? So we have to take out half a unit less and half a unit more. So half a unit less, half a unit more, we'd have to go one more decimal place over, which would be the hundredths, and we will add that hundredths and subtract that hundredths, the half unit being that 5. So adding the 0.05 to it, we'll have 28.35. That's our max. And if we subtract that half unit from it, we'll have our minimum, which will be 28.25. So think of it not like 3, but think of it like 30. And when you take 30 and add 5 to it, you're at 35. When you're at 30 and take away 5, you're at 25. So that's where you get the minimum lengths and maximum lengths there. Now let's talk about width, because width is different. And I like the fact that it's different. It might help you understand this a little bit better. So width is just 21 centimeters, right? But we have to go one more decimal place further. So we have to go into the tenths. And that's where we'll both subtract the 5 and add the 5, because we're going one place over. Then we add and subtract that from our 21.0 plus the 0.5 and 21.0 minus the 0.5. So it's very important we understand the difference. Why is it we did 0.05 up here, but we're doing just 0.5 here? And that's because this first one went to a tenths place, so we'd have to go to the hundredths place to add and subtract. Whereas this one went to the ones place, so we'd have to go to the tenths place to add or subtract, because we always just go one unit further down the line. All right, I'll do a couple other examples as well to kind of make this a little bit more clear. But anyway, when you add the 5, subtract the 5, you have 21.5 and you have 20.5 as your minimum and maximum lengths. And so when you find the area, once you have these lengths, you can find the area by taking the maximums and multiplying them together. So the maximum area, you take the maximum width and the maximum length and you multiply them together. You do the same thing if you want to find the minimum area. You take the minimum results and you just multiply them together to get the minimum area. So you can see that the minimum area was 579 because you just multiplied those numbers together, and the max was 610. So that means the area is somewhere between 579 and 610. Let me just take some time before moving on to address this whole half unit thing again. Okay, so I'm gonna erase this. You can always, rewind the video if you ever wanted to see any more of it. But this can be, I can already kind of tell this is where some people are gonna get a little bit lost. So let's say I had, I'm ignoring this problem completely, by the way. I'm just making up some numbers. Let's say I had a number that I was measuring. It was, let's say it was 55.23, right? That's the number they give to me, and I have to look at the min and max here. So a half unit more and a half unit less. Well, this one goes to 2 decimal places right now, right? It's 2 places to the right of that decimal. So I have to go 1 more place over, and that's where I'm going to put my 5 to add or subtract. It's always 1 more place over to the right, 1 place further. So you would, in this case, if you had this type of number, you would add and subtract the 0.005. If you had, let me make up another example here, okay? Let's say I have 76.294. This one goes all the way to 3 decimal places. So I'd have to go 1 more place over, so 4 decimal places, to add and subtract my 5. It's always 1 unit further in, okay? So in that, I would add 0.0005 to this, and I would also subtract 0.005 from this to get that max and that min. Okay, so whatever decimal place it is, you have to go 1 place further over. So if I just had the number 80, for example, right? Well, 8 is the last real significant number here. So I would go to the place over, which the 0 is already there. But I would go for this place because it's just 0. Remember, 8 is the only significant value. And that's where I would add and subtract 5. I would add and subtract 5 in this one because it's my tens place is where my number is. So my ones place will be where I add and subtract my value. So that would be your max and min there. If I had 83, right, the ones place is my significant value. So I'd have to go 1 place further over into the tens to do my half digits. Okay, it's always 1 place more. So again, so let's look at this example, and we'll see if that if maybe you start understanding it when we look at it another problem. So the length and width of a rectangle are 15.5 centimeters and 10 centimeters respectively. So let's look at the 15.5. So the 15.5 goes 1 decimal place in to the tenths place. So when we add and subtract a half unit, we're going to have to go 1 more place further, and that's where I'm going to put my 5. So my 5 will be in my hundredths place, because remember, it's always 1 place further over. So now you add the 0.05 and you subtract the 0.05. So when you add it, you'll have 15.55, and when you subtract it, you get 15.45. So here, to fill this in, the half unit will be the tenths place. So we're subtracting the 0.05, we're adding the 0.05. That's what I just did over here. but I'm just going ahead and writing it into the blanks. So the lengths are, the minimum is 15.45 to the maximum, which is 15.55. That's how I found them. I went one decimal place further over. So now let's look at the centimeters one, the 10 centimeters one. So we have 10 centimeters. Okay, now the 1 here is the significant value. Okay. Hold on now. I'm seeing something. And I might have said something wrong earlier when I said the 80. So backtrack. If you saw what I said with the 80 earlier, that was incorrect, and I apologize for that. The 0 actually does matter here. Oops, it keeps moving every time I put my hand on the screen. So 10. The 0 is actually the significant value. It's not really considered a significant value, but for the purposes of these half units, it is. So 10 is our number, and so it ends, I guess I really shouldn't use the word significant value. I should just say where it ends. It ends in the ones place. So we have to go 1 unit further in to the tenths place to put our 5 that we're going to add and subtract. So it's not where the last significant digit is in this case. It's where the last digit is, period. So the last digit in 10 is the ones place. So 1 place further over will be the tenths place, that 1 decimal place over. That is where we'll put the 5, and that is what we'll add and subtract from. So when we add the 5, we'll have 10.5, and when we subtract it, when we subtract the 5, we get 9.5. So we're subtracting and adding just regular 0.5. So making our smallest one, going from 9.5 to 10.5. So I apologize for that confusion. So if you want another just quick side example, let's say back to the number 80 that I showed you earlier. The 0 is the significant, well, I shouldn't say significant, but 0 is the last digit. So you would go 1 place further over, which would be 10 point or 80.0, and that place is where you'll put your 5 that you add and subtract. So for that 80, you would actually have 80.5 as the top, and when you subtract, you would have 79.5 as your minimum. So that's nothing to do with this problem. I just wanted to mention that because I said it earlier, and I wanted to fix it. So now the minimum area, we take our smallest values and multiply them together. So the 9.5 centimeters times the 15.45. So 9.5 times the 15.45. And we get 147 centimeters squared. And then for the maximum area, we take the bigger value. So that'll be 10.5 and 15.55. So 10.5 times 15.55. And that'll be our maximum area, which will be 163 centimeters. Remember, you're just multiplying those together. So our area is anywhere between 147 and 163. Okay. So if you feel like going for it, you can try these examples 3 and 4. You can pause the video, try and work them out, and then continue the video to see the solutions, or just watch through the solutions. It's up to you. I would encourage you to try it on your own because it's the best way to learn. Watching me isn't going to really, it wouldn't help you learn as much as trying to do it yourself. Okay? But anyway, I'll give you a second to start, and then I'll work it out. So you pause the video if you feel like you want to try them on your own. Okay, so Sarah wants to paint a wall. The length and width of the wall are 2 meters and 1.4 meters respectively. So let's focus our attention on the 2 meters. So 2 meters is just 2. That digit is our ones place. One digit over will be in the tenths place. That means in the tenths place is where we're going to put the 5 for adding and subtracting. So if we add the 5, we'll have 2.5. And if we subtract the 5, we have 1.5. Now, same thing for the 1.4. So 1.4, its digit ends at the tenths place. So we have to go one digit further to the right, and that is where we'll add and subtract that 5 in the hundredths place. So adding it, we'll have 1.45, and subtracting it, we'd have 1.35. So our minimum lengths for minimum is the 1.35 and the 1.5. We'd multiply those together to find our minimum area. For our maximum area, we take our bigger lengths, which is 1.45 times the 2.5. And we get our maximum area. So the min and max area would be 2 meters squared and 4 meters squared. So that means the area of this wall that we have to paint is anywhere between 2 meters squared and 4 meters squared, which is actually a pretty big difference if you ask me. But yeah. All right, so look at number 4. So again, pause if you saw that and maybe you want to try, maybe you didn't, try it on your own, or maybe you want to redo number 4. I'll give you seconds, pause the video and try number 4, and then we'll talk about number 4. Okay, so 15 feet. 15 is in our ones place. So one digit over would be 15.0, and that tenths place is where we'll put the 5 that we add or subtract. So we'll add the 0.5, we'll have 15.5, and then we'll also subtract the 0.5 to have 14.5. There's our minimum and our maximum for the length, and now for the width, let's go a little further over. We have 22.7. So the tenths place is our last digit. We have to go one place further over, and that is where we'll put the 5 that we add or subtract. So we'll add it, and we'll have 22.75, and then we'll subtract it, and we'll have 22.65. So now for the minimum area would be the smaller ones multiplied together, 22.65 times 14.5. And our maximum area will be for the maximum length and width. So that's 22.75 times the 15.5. And so the result here is, let me check, 328 square feet and 353 square feet. So it's anywhere between 322 and 353. Okay, I'm going to end the video here because the next one's going to be talking about significant digits. So I'll see you guys in that video. All right, bye.